Okay, back to the lab. We're doing lab class 10. It's the 6th of November, 2021. We're talking about predicted probabilities and ROC. We are using the RMD file for the lab, which is S10 lab 10 RM lab 10 RMD. So we will slowly go through. So I have uploaded lab 10 class R and lab 10 addition.R. So these are the actually codes from Marcel and Bino. We have here lab 10. We see an RM list equals LS. This is clearing the environment, which we have now here. This is a library ISLR, which is Intro to Statistical Learning, that will essentially give us access to data, which seems to be here, data with 10,000 entries. If we look into head default, it actually gives us here an overview of this data. We have here a balance, we have income. So this is the data set we're going to be working with. Table default. We can look into the documentation of our data set, which essentially is here. Predicate default data, 10,000 observations and following for variables. Factor with levels no and yes. Customer defaulted on their debts. So it's the defaulting on your debts. Student, whether the customer is a student or not. The balance on the remaining on the credit card. Right, that's quite a hefty kind of predicate debt, and then the income of the customer, which is here stated on the right. So sources simulated data. Yeah, I was hoping this is simulated data. Having this amount of depth is definitely not very healthy. Okay, fit 0 is essentially the fit. So we have defaulting yes, no as a function of student yes, no, which essentially is here. Summary fit 0 turns out to be a significant predictor. Summary fit is that one we actually have. That one we have. So we have summary fit. Summary fit. This is essentially balance is another predictor. Being a student is 1, 2. Histogram shows you now if we're predicting, if you're using here the predict function, if we're using a prediction of the probabilities using the predict function, essentially gives us here a list of these probabilities that are essentially individual for each individual entry. So these probabilities essentially allow for a probability prediction of each individual participant, or that, in that case, every case entry. So if we have threshold, so now we essentially want to determine thresholds for our ROC construction. So we essentially have probabilities that are essentially based on this prediction function on our prediction models, our logistic regressions up here. So we are now building a threshold sequence vector that essentially contains thresholds for each 0.01. So essentially this will allow for us to now build this vector. So now sensitivity and specificity are now here NA entries. So this is now, we have now two additional vectors, which is sensitivity and specificity. And we are now, and this is a so-called for loop. So a for loop essentially is, and we have seen for loops in the past. So this is essentially from I to sequence of threshold sequence. So threshold sequence is 101 entries long. And we're getting with sequence along threshold sequence from 1 to 101. We essentially create this vector. So it will go each item through this vector, and it will give, for each iteration, it will assign this entry to I. So now in decision, so let's assume we're taking I equals 3, just as an example. So let's assign, so this is from 1 to 101. It will run through that I. So if we are now defining decision will take now a probability that is greater than threshold sequence I. So threshold sequence I is now 0.02 because it's the third entry, right? So we have set I equals 3. So now it takes the third entry of threshold sequence. So this is 0.02. Then it will create my YT, and this is the same as in the lecture. And my YT will essentially calculate now exactly this decision table. Based on this decision table, we are calculating now decision equals 0 and default equals no. Those are true negatives. And D, these are true positives. So based on that, essentially, it will now calculate specificity and sensitivity. And it will assign it to each entry. So here we have the third entry is now the respective sensitivity and specificity for that point, for this particular entry. So if we are running the whole thing, we get now, as a consequence of running these loops, we are getting now all sensitivities and specificities along the entire range of decision entries. So this means that now we can calculate the true positive rate, the 1 minus the specificity. And by that, we can, now if we do head spec sense, is essentially, this is, so we have a sensitivity of 1. This is where sensitivity starts. Then 1 minus specificity, this is where specificity ends, right? So this is the endpoint of the ROC. Remember how the ROC looks like. So this is our endpoint. This is absolute sensitivity and specificity. So we want, now this is absolute sensitivity minus 1 minus specificity. So this is this point here. And then essentially it will change according to the threshold that you're choosing. So if you're building now this, essentially you get the entire the entire data set shown. And if you're plotting now these codes, you essentially get here the ROC curve depicted. So the plot function essentially shows here on the x-axis everything. So here we have x and y plot. So it's separated by a comma. So everything before the comma is here the x, whereas everything after the comma is the y. Xlim defines the limits on the x-axis. So this is 0 to 1. Ylim is from 0 to 1. Type is a line type. Color is red, which essentially is here not red anymore. But let's wait a second. So this is the red one. So this is here the labeling X lab and Y lab. Then here we have our blind. And this is our air blind, that is the line of identity. And now we do a main. Main equals ROC curve, could also have gone here, but it's sometimes better and easier to show it separately. Spec sense. I'm not sure why there's a second entry in that regard. I'm not sure I'm seeing that advantage, but okay. You could also separate this out from this, and you could overwrite it also in yellow if you wanted to. I don't like it in red. Specificity and sensitivity. Yeah, so there obviously there's also different ways of depicting that. There is, for example, also the PROC dataset, library PROC. I'm just flagging this because it is a fairly good package. And with ROC, you can also essentially, please check it out, because sometimes it also can be helpful to look at alternative packages. So with predict and response, you can actually depict both in the same fashion. Gives you also with optimal, it essentially can also give you then BIOS plot smooth method density. It's also in the same package. You also have the generation of the optimal threshold, which is something where various methods exist. One common method is the so-called Yalden index. And these are different constellation pieces. So this is essentially what we have for the lab. So you can always, you can here also, so you have here this model. This is essentially the same. We are looking, so this is the documentation contrasts. We have this. We have these models. We have here exactly this overview. We have true positives, true negatives. Just always be careful. You are, So here's exactly happening what I mentioned before. So Marcel and Bino used different kind of way of depicting it in the 2x2 table. So here the true positive is actually here, the A, and the true negative is actually here, the D. So, but keep in mind that you always have the condition actually on the columns, and you have a diagnostic tool, whatever this is, a method or a logistic regression on the rows. And you need to calculate 1 minus specificity. So now specificity is true negative divided by true negative and false positive. So this is here, this condition. And on your x-axis, you have the false positive, right? So this is 1 minus specificity. And you have on the y-axis, you have sensitivity. Sensitivity is true positives divided by false negatives and true positives. So just make sure that you go step by step through this code. Make sure that you understand that code. Okay, I need to rerun this. Come on. Okay, so. These are the probabilities. Now you can go through the probabilities and you can calculate the spec sense. Yeah, you can in addition to that, you can here do alternate kind of calculations. You can use lowest smoothing. So smoothing is always an approach where you essentially use localized knot points to essentially smooth out curves. And so if you're using here coef unique default, true positives is length, true positives. So you are here, sequence along, x tab, yes, divided by some tab. So you're creating here true positive and false positive aspects, and you are essentially using the same to build here lowest smoothed curves, which are here essentially smoothed as compared to the other approach, the raw depiction of your, and you see how it smooths out, right? You see how you actually lose the granularity of these individual scores that are changing the shape and appearance of the curve. It smooths it out. You can then further compare AUCs between various methods and between models. There are various ways to do that. AUC is one of those ways to do that. You can calculate from that AUC, in addition to that, also confidence interval. So you can also do formal testing with your resulting AUCs. So you can compare not only logistic regression models, you can also use this for methods, measurement methods. You can use, for example, with the AUC, it is essentially, it's a way to kind of characterize diagnostic performance in comparing methods or models in the predictive quality. And it's usually, it's a quite common way of doing that, particularly in the realm of data science. You will essentially use AUCs to judge the quality and accuracy of your models. And this is quite a common approach to do that. So you have, okay, so this requires quite some computation time here. Which is interesting. Seems like it is quite a laborious computation, but it's also that the data set is quite large with 10,000 entries. So this likely makes it quite intense. So now it's finished. So if you look now at TP and XTab, you essentially have now you're comparing now, you get now TP and COF. You are indicating on TP and FP at TP. You have now essentially entries that are smoothed by the local entries, to my understanding. Some X tab. So we're getting here X tab, table defaults for unique P default. So we're with default. P default with 10,000 elements. We are getting here X tab. If we are setting this sec along COF is unique P default, COF should then be again 10,000. So we have now in COF, we have individual entries, which is avoiding redundancy, but it's still 10,000, so that was unnecessary. Then we have true positives and negatives, and then we're creating here P defaults is greater than COF. This is our def Y is here with our thresholds from P default. We are essentially getting zeros and ones, depending on whether the default or not. And here we're building these tables, and the tables are essentially now calculating probabilities in the same fashion. So we are calculating here X tab. This would be true positive divided by true positive and false negatives, whereas false positive would be, so it's basically, it's an alternative calculation, which took a little longer, but essentially it comes to the same end as the previous one, as the previous for loop that we did earlier, this here. It comes to the same kind of way. And now with the lowest, we're plotting now the ROC curve. We did that. We are implementing, so we get plot here. So builds the axis here. And then we're getting segments. Okay. Okay. And we're getting segments of X0 and Y0. Lowest will then basically plot the false positives as a function of the true positives as a function of the false positives, and this will essentially standardize it with the lowest algorithm. Low. Lowest, okay. So we're creating here a new data frame, lower. This is essentially the smoothed algorithm that essentially starts here, play then kind of also allows for a smoother overview and the smoother appearance as compared to the raw score entries. Okay, so you create with the lowest function, you create a new vector here using the false positives and the true positives, and then you essentially, you're taking these probabilities that were calculated here to basically get these entries, get these data points. Then you calculate area under the curve, heights of individual parallelograms. Can compare models, okay. Okay, you can now len and age. So the length of the individual parallelograms means it's essentially using this to calculate the area under the curve by hand from height and length. And this is, I will, in addition to that, post also Marcel's explanation of the topic. If I can find this on YouTube that I can actually post it. Because I myself not entirely sure how this, I've never done this by hand, to be honest. Because there are essentially different ways to calculate areas under the curves. But yeah, by calculation of this area under the curve, you get this area under the curve, under the ROC curve. And you essentially can use this to compare models to each other. So if you are essentially using alternative models, you can essentially use different approaches. But so essentially you're being asked at this point to use the admit data, fit a prediction model with admit as the response variable to predict being admitted using GRE, GPA, rank, and the interaction of GRE and GPA as predictors. You obtain the probabilities like we did up here with prob, right? You remember? And you can, based on that, you can for each value calculate two vectors, sensitivity and specificity, using here this threshold vector that is given here. And then you can plot 1 minus specificity versus sensitivity. Okay, so good luck. And I will post an alternative code using the pure package to calculate the AOC. And I will also additionally post Marcel's explanations of this code. Okay, good. So see you next week. And good luck with this lab.